Today, we are pulling back the curtain on your computer's processor. We're going to get right into the nuts and bolts of the incredible engineering that makes modern computing even possible. We're talking about pipelining and superscalar design. So, have you ever really stopped to think about how your phone or your laptop can do so much, so fast, all at the same time? I mean, the speed is just mind-blowing. But it's not just about raw power or shrinking transistors. The real secret sauce is this incredibly clever trick that works a lot like a factory assembly line, but for tiny bits of data. All right, so here's our roadmap. We'll kick things off with the basics. What even is CPU pipelining? Then we'll dig into how we measure its performance and see what happens when those pipelines start getting a little more complicated. We'll also look at the traffic jams or hazards that can grind everything to a halt. And finally, we'll see how all of this evolved into the powerhouse superscalar processors we all use every single day. Okay, let's jump right in. Section 1. It all starts with this core idea, the assembly line for instructions. This is the concept that completely changed the game for processor speed. A linear pipeline is, well, pretty much exactly what it sounds like. It's a series of processing stages, all lined up one after the other. So instead of having one big, complex unit try to do a whole task from start to finish, you break that task down into smaller, simpler pieces. Each stage in the line becomes a specialist, doing just one small part of the job over and over. Now, you've got to manage the flow of work down this assembly line, and there are two main ways to do it. On the left, you've got the asynchronous model. Think of it like a very polite system where each stage finishes its work, passes it on, and then waits for a thank you or a got it before taking on more. It works, but it's slow. That's why pretty much all modern CPUs use the synchronous model you see on the right. In this system, there's a central clock that acts like a relentless factory foreman, basically yelling next at perfectly timed intervals. Everything moves in perfect synchronized lockstep. It's all about maximizing throughput. And this reservation table, this is where we really see the magic of pipelining in action. Check out where the X's are. At clock cycle 1, our first task enters stage 1. Okay, simple enough. But here's the key. At clock cycle 2, that first task moves to stage 2, and a brand new task immediately enters the now empty stage 1. So by the time our first task is finishing up in stage 4, there are 3 other tasks right behind it, all being worked on simultaneously. It's this constant overlapping that gives us that huge boost in speed. We're always working on 4 things at once. So, okay, this definitely feels way faster, right? But how do we actually measure that performance gain? How much faster are we really talking? Let's crunch some numbers. You know the saying, a chain is only as strong as its weakest link? Well, a pipeline is only as fast as its slowest stage. This formula tells us exactly why. The total time for one tick of the clock, that's the Greek letter tau, is set by the time of the slowest stage, that's tau m, plus a tiny bit of overhead called latch delay, that's d, which is just the time it takes to hand off the work. So even if you have a bunch of lightning-fast stages, everyone has to wait for the one slowpoke. So that brings us to the big one, the speed-up factor, SK. Now, this formula might look a little intimidating, but the idea is actually super simple. It's just a comparison. T1 is the time it would take an old-school non-pipelined processor to do the job, and Tk is the time it takes our shiny new pipeline with k stages. You just divide the old, slow time by the new, faster time, and you get a number that tells you exactly how much of a speed boost you got. Okay, let's make this concrete. Say we need to process 64 different tasks. That's our N. And we're using a CPU that is an 8-stage pipeline. That's our K. You run those numbers through the formula, and what do you get? A 7.2 times speed up. That is a massive, massive gain. And remember, we didn't make the chip itself any faster. We just organized the work in a much, much smarter way. And what's really cool is shown in this graph. It shows us the theoretical limit. As you throw more and more tasks at the pipeline, that's N getting bigger and bigger, the speed-up factor, SK, gets closer and closer to K, which is the number of stages you have. So an 8-stage pipeline, that bottom curve, can theoretically get you an 8x speed-up. A 10-stage pipeline, the top curve, approaches a 10x speed-up. It's the ultimate goal, even if you never quite reach it perfectly. But of course, the real world is messy. Tasks aren't always so straightforward. The assembly line doesn't always go in a perfectly straight line. So what happens when that line needs to bend, or even loop back on itself? This is what we call a dynamic or nonlinear pipeline. See those arrows?
You've got connections that can skip stages or even loop back to earlier ones. This makes the pipeline incredibly flexible. It can perform all sorts of different functions. But that flexibility comes with a huge new headache.
And that headache is called a collision. Let's just walk through this reservation table to see what I mean. Task 1 starts at time 1. It goes through its steps, but at time 7, it needs to loop back and use stage 1 again. Fine. But what if we launch a new task, task 3, 5 seconds later? Well, at that same exact moment, at time 7, task 3 is just starting, and it also needs to use stage 1, and boom, you have 2 different tasks trying to use the exact same machine at the exact same time. That's a collision. The whole assembly line just grinds to a halt. So how do you prevent this? Well, engineers came up with a clever tool called a collision vector. It's really just a simple binary code. For every possible time gap you could leave between starting new tasks, it gives you a 1 if that gap will cause a crash, and a 0 if it's safe. It's basically a little cheat sheet for the processor that acts like a traffic light, telling it exactly when it's safe to let the next instruction onto the highway.
So these collisions are a big problem. But when we're dealing specifically with computer instructions, there are even more subtle kinds of traffic jams we have to watch out for. We call them hazards. And there are 3 main flavors of these data hazards. First, you have read after write, which is pretty intuitive. An instruction tries to read some data before the previous instruction has finished writing it. Then there's write after write, where 2 instructions are racing to write to the same spot, and the wrong one might win. And finally, write after read, where an instruction overwrites data that an earlier instruction still needed to look at.
These diagrams really help clear it up. A read after write, or a true data dependency, is simple. Instruction J just plain can't start because it's waiting for a result from instruction I, but the others are sneakier. A write after read hazard, or anti-dependency, is a real problem. It's when a later instruction, J, is about to overwrite a value that an earlier instruction I hasn't read yet. If J goes too soon, I is going to grab the wrong data, and your entire calculation goes haywire. Getting this timing wrong can cause catastrophic errors. So managing all of this complexity, all these hazards and collisions, is absolutely crucial. And learning how to manage it is what allowed engineers to push the whole pipeline idea to its absolute limit, creating superscalar and super pipeline architectures. This little table breaks down the difference perfectly. A standard scalar processor is our baseline. It issues 1 instruction per clock cycle. A superscalar processor thinks wider. It has multiple execution units, so it can issue M instructions at the same time in 1 clock cycle. A super pipeline processor thinks deeper. It splits the pipeline into even more, tinier stages, so its clock cycle becomes N times faster. Both get more work done. They just take different approaches. One goes wide, the other goes deep. And this is what a superscalar processor actually looks like inside. It's not just one pipeline anymore. You can see multiple pipelines and all these specialized units for different tasks, one for adding, one for multiplying, one for logic, all humming along in parallel, working on different instructions at the exact same time. So if you remember just one thing from all of this, let it be this simple idea. Pipelining turned the processor's job into a high-speed assembly line. And then superscalar architecture took that amazing idea and said, why have one assembly line when we can have a whole factory of them, all running side by side? It's that powerful 1-2 punch of efficiency and parallelism that really drives the modern digital world. And that just leaves us with one last big question to think about. We've pretty much perfected these pipelines for our CPUs, but now, as our demand for data just explodes with things like AI and massive machine learning models, what's the next revolutionary assembly line for computing going to look like? What comes next?